The last session of the morning. The speaker is Werner Stuetzle of University of Washington. So he will talk on nonparametric cluster analysis, estimating the cluster tree of a density. Okay.
Thank you. Can you all hear me? Does this thing work? All right, so first of all, I want to thank the organizers for inviting me and giving me the opportunity to give this talk. This is joint work with my student, Rebecca Nugent. All right, so this is a talk about cluster analysis. So let me first talk about what the goal of clustering is. So the goal of clustering is to detect the presence of distinct groups in a collection of data, vaguely stated. So then, of course, you have to ask what do you mean by distinct groups? So the definition that we're going to adopt here is, by distinct groups, we mean contiguous and densely populated areas in feature space separated by contiguous, relatively empty regions. So I have a couple pictures here which illustrate what this could mean. So, well, here we obviously have two dense regions separated by an empty region, ditto here, ditto there. Now, this kind of structure is not covered by this definition, right? So although anybody who looks at this would say, well, there are actually two distinct groups in the data, it's not covered by this definition. I think it is actually very difficult to come up with a definition of groups that would cover whatever one might visually perceive as groups if one were looking at a two-dimensional picture like this. I think this would be very hard to do. So before I go on to the more technical parts of my talk, I want to make a couple of remarks on clustering versus classification. So clustering, also called unsupervised learning or concept formation, the goal is to find groups in unlabeled data, in contrast to classification or supervised learning, where the goal is to find a rule to label new data or new and unlabeled data based on the training sample which you are given the group labels. So most of the talks in this conference so far obviously have been on classification or supervised learning. In general, I think the methodology for supervised learning is much better developed than for unsupervised learning. And there are several reasons for this, I think. First of all, supervised learning is a more important problem. Now, why is that so? Well, supervised learning involves prediction, and very crudely speaking, if you can predict, you can make money, right? I mean, that's a very crude way of looking at it. Another reason why I think there has been more progress in research on supervised learning is it's easy to define and to measure the performance of prediction rules. So, and measuring performance of a procedure is very important to make progress, right? Because if you can't measure performance, right, the concept of progress doesn't really even make sense, right? So being able to measure performance is a critical thing. And so in supervised learning, you can always do that. And for any given data set, you can do cross-validation, or you can divide it into a training set and a validation set, and you have an objective way of assessing performance of procedures. You just look at the misclassification rate, and if mine is better than yours, then I win, right? This is quite unambiguous. And then the last point, this is the main point I want to address today, is that there is actually a lot of work on clustering in the machine learning literature, some in the statistical literature and in other areas, but most clustering methods are stated algorithmically. So stating algorithmically means you just have a procedure while you plug in the data on one end and clusters come out on the other end, and often there is no concept of estimating any underlying population characteristic, right? And so then, if there is no concept of estimating a population characteristic, it's of course hard to measure how well you succeed, right? So this is sort of another aspect of the second issue I'm addressing here. So most of my talk today, will be about thinking about what kind of population characteristic might we actually want to estimate. Okay, so I'm going to talk about statistical approaches to clustering. Okay, so just briefly to sketch the problem. If we had a two-dimensional data set like this, what we want to detect is we want to say, well, there is 5 or maybe 6 groups, 1, 2, 3, 4, 5, maybe this one here, and we want to assign group labels to the observations. So what we need to specify is we need to specify a sampling model. How did the data actually arise? And the population characteristic of interest. So without a sampling model, i.e. the data are sampled IID from some underlying density, without a model like that, it doesn't even make sense to talk about cluster validity, because validity somehow implies, right, from the points that I actually have, right, what can I conclude on some underlying population? Well, you can only do that if you have some idea about how your observed data actually arose from this population. Okay, so you need a sampling model, and without the population characteristic of interest, you can't really evaluate and compare clustering methods, right? And so that means it's questionable if it even makes sense to talk about progress. So the sampling model in this talk is very simple. I'm just assuming that the feature vectors that you actually observe are IID from some density P of X. Okay, so now let's think about what statistical approaches to clustering are there. And I'll distinguish between parametric and the non-parametric approach. So a parametric approach, the most common one is called model-based clustering. So model-based clustering is based on the premise that you have groups in your data. Each group corresponds to some member of a parametric family, typically the multivariate Gaussian distributions. So if you have a bunch of groups, each group has a multivariate Gaussian distribution, right? Then the data that you observe just comes from a density which is a mixture of the group densities P sub G with this mixture weights pi sub G, and you have capital G groups here, so capital G mixture components. So well, if you're working under this assumption, then for any given number of groups for any given G, you can just find the group means and covariances using the EM algorithm, and you can estimate the number of groups, for example, by cross-validation or BIC or other criteria. And once you have done that, then you can label the observations using Bayes' rule. Now, the model-based clustering has a number of strengths. One is it's an intellectually coherent approach, which also gives you a way to estimate the number of groups. And it can be extended in various ways. For example, you can allow for background noise. So basically you have models for, you have density, you have the group densities of individual groups. You can make some model for the background noise, and then you can basically pull apart the groups themselves and the noise. And it has been extended in various ways, in other ways, for example, multinomial mixtures in the context of document clustering. So Gaussian mixtures aren't the only ones that are being considered. For example, multinomial mixtures have been considered as well. So this is all good about model-based clustering, which is actually a very successful procedure in practice. However, it has a weakness, which I think is shared by all parametric procedures. It can lead to unexpected results if the assumptions are violated. So here is an example. Here is two data sets, data set 1 and data set 2. Now, I think anybody who would look at those two data sets would think, well, in both cases, there are two groups in these data sets, right? Obviously, right? So now the way I made the left data set is just a sample from two Gaussian distributions. The way I made the right data set is actually similar. I just adulterated the distributions a little bit, right? So now, if you run this model-based clustering and you use this BIC criterion to estimate how many mixture components you want, well, for this data set, well, because the two groups are from Gaussian distributions, well, the procedure works well. It tells you get two mixture components, and this is the groups that you find. However, if you apply the same procedure to this data set here, well, these groups are not Gaussian, right? So when you try to model them by Gaussian mixtures, right, as it turns out, you get two mixture components for this set of points here, and two mixture components for that one. So 4 mixture components total, right? Although anybody would think, well, there are really only two groups in this data, right? Okay, so this is just to make the point, right, that if you make the assumption that your groups are Gaussian and the groups are not Gaussian, right, the results can be misleading and not what you would expect, right? Another, of course, weakness of this Gaussian mixture modeling is it can't handle non-elliptical groups, right? For elliptical groups, that's fine. For non-elliptical groups, this isn't going to work well. Okay, so now I'm going to talk about the non-parametric approach, which is the one I'm going to pursue in this talk. And the non-parametric approach is based on the premise that groups correspond to modes of the underlying density of the data. So this was an approach that was pioneered by John Hartig, and he and his students did a lot of early work in this area. And so he's basically the father or the grandfather of whatever I'm going to talk about next. So the goal here was also stated, I think, in a very nice way by David Wishart in a 1969 paper. He said, clustering methods should detect and resolve distinct data modes independent of their shape and variance. So basically, you should be able to detect groups which are non-elliptical in distribution, for example. Okay, so if you want to pursue this approach, right, you need to do two things. First of all, you need to estimate or find modes of the data density, right? And then you need to assign each observation to the domain of attraction of a node. And I put domain of attraction in quotation marks here because it's a very vague concept, but I'm going to make that more precise in a moment. So in this talk, we'll pursue this non-parametric approach. Okay, so what's the population characteristic of interest now? The population characteristic that we're going to try to estimate is the cluster tree of the density. So the cluster tree is defined in terms of level sets. So the level set L of lambda and P of a density P at level lambda is the subset of the feature space for which the density exceeds lambda. Okay, so just to illustrate this, here we have a density. Actually, I just simply made a mixture of three Gaussians, two high peaks and a low peak here, right? And now we're going to look at the level sets. Well, so we have this mountain, and we're just going to intersect it with the plane at height lambda, and we're going to look at the intersection, and then we're going to move lambda up, right? Okay, so let's just look what happens here. Well, so for small lambda, this is what you get, right? Then as you increase lambda a little bit, if it moves above the valley that separates this peak from the other two, right, you get these two connected components here, right? So one corresponding to those two peaks and one corresponding for this one. Well, you keep lifting the level up, right? And then eventually the level is going to be above the height of this peak, and this connected component will disappear. Right? Well, so then you move further, right? And then eventually, once you move above the valley connecting between those two peaks, right, then you get the two connected components here. And if you go further on, eventually you get the empty set, right? If your level is above all the peaks. Okay, so two things I want to point out here, which are kind of obvious. First of all, level sets with multiple connected components indicate multimodality. And a second important observation is that there may not be a single level that actually that reveals all the modes, right? See, there is one level here which reveals this mode here and separates it from the other two, right? But then there is a different level which reveals those two modes, right? But then you don't see the third one in this picture here, right? So the message is very simple. The message is you need to look at level sets for all levels. Just picking a single level is not enough. Okay, so John Hartigan early on pointed out that the connected components of level sets have a tree structure. By that I mean that for any two connected components, possibly at different levels, let's say the components are A and B, either A is subset to B or B is subset of A, or the intersection is the empty set. So these level sets have a tree structure. The connected components of level sets have a tree structure, and that tree structure is summarized or described by the cluster tree. So I now want to define what the cluster tree is, and I just picked, to illustrate this, I picked a very simple unimodal density here, and now I want to define what the cluster tree is. So the cluster tree is easiest to define recursively. Each node of the tree represents a subset of the feature space and is associated with some density level lambda. So D of n is the subset of the feature space associated with node n of the tree, and lambda is the corresponding level. The root node of the tree represents the entire support of the density and associated with level lambda equals 0. Okay, so to determine the descendants of a node n, first of all, we find the lowest level. Well, actually, I'm not even going to read this. It's going to be obvious when I just tell you what happens. Okay, so we start with level 0. We have the root node of the tree here corresponds to level 0. Okay, we move the level up, 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 and then once the level reaches here, we get two connected components, right, of the level set. One connected component here and one connected component there. Okay, so we generate two daughter nodes of the root node at that level where the split happens, and then we just recurse the procedure. So if in the recursion we first treat this connected component here, we move the level up, 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 up. There's no further split, so this is a leaf of the tree. Right? Then we recursively process the left component of the left connected component. We move up, up, up. Well, eventually we get here, right? We find two connected components again. We generate two daughters of this node, right, at that corresponding level here, right? And then again we have a split, so we recurse. There is no more splits here. There is no more splits there. So that's the cluster tree. Right. All right. So the cluster tree is what we're going to try to estimate. Right? So basically, the cluster tree summarizes the connectivity structure of the connected components of the level sets. Right. Okay. So here is the example again. So this is the same density as we had before. This is the cluster tree with its interior nodes and leaves, and these are the corresponding areas of the feature space associated with each of these nodes, right? So the two leaves here, they correspond to these two high peaks here. This leaf corresponds to this peak here, and then the gray area corresponds to where the level just is above the valley between those two curves. Okay, so the leaves of the cluster tree correspond to modes of the density. An important thing, which can be either good or bad, is that the cluster tree is invariant under non-singular affine transformations of feature space. By invariant, I mean the topology stays the same, the levels will change, right? But the topology of the cluster tree stays the same. It's invariant under non-singular affine transformations. And so the cluster tree is the population characteristic that we're going to try to estimate. Okay, so now the question is, how do we estimate the cluster tree of a density? So we have a sample from some density P of x. We want to estimate P of x. Well, so there is an obvious idea, which is to use a plug-in estimate. So by plug-in estimate, I mean we compute some typically non-parametric estimate of the density P hat, although any density estimate will do, and then we just estimate the cluster tree of the unknown density P by the cluster tree of the density estimate P hat. So this is a simple recipe. However, there are computational and statistical problems with that. The computational problem is, well, so how can you actually compute level sets and their connected components? Just think you have 10-dimensional feature space. You have a function over 10 dimensions, right? And the function may not be given in any kind of analytic form to begin with, right? And now you want to find level sets of this function and their connected components. So this is not totally obvious how this can be done in general, right? So this is the computational problem. How can we compute level sets and their connected components? And then there is a statistical problem also, which is whenever you compute a density estimate, right, just because of sampling variability, right, there will be, it may have many modes, right, which are just due to sampling variability, right? So somehow you've got to try to pull apart the modes that just come from sampling variability from modes which are due to actually structure in the underlying density. So that's the statistical problem here. Okay, so I'm going to address the computational problem first. So how can we actually implement this recipe? I mean, how can we actually compute the cluster tree of a density estimate, right? Well, for some density estimates, you can actually do this exactly. For example, for piecewise constant density estimates. So for density estimates that are piecewise constant over rectangles, so the rectangles here are R sub I, the values of the density estimate in the rectangle R sub I is C sub I. They are little m rectangles. So if your density estimate is of this form, then it's fairly obvious that you can compute level sets, their connected components, and the cluster tree exactly. That's just a very simple computational problem. Now, what kinds of estimates are piecewise constant? Well, obviously, histogram estimates are piecewise constant. Average shifted, David Scott's average shifted histogram estimates would be piecewise constant. Moreover, in principle, you can take any density estimate and you just discretize it, right? You just bin your feature space, right? And then you approximate your estimate by a piecewise constant estimate. So the problem is, of course, that this is really only viable in low dimensions, let's say less than or equal to 4, because I'm sure everybody here knows you just can't bin high dimensional space, right? There are too many bins, and so that's just not a viable recipe in high dimensions. Okay, so then the question is, well, so what do you do if you are in high dimensions and you don't have a piecewise constant estimate? Well, so what you have to do is, you don't have to. The only solution I know is to use approximations, right? So if you can't compute the cluster tree exactly, maybe you can use some approximation to do so. So the approach that I'm going to suggest is a graph-based approach for approximating the cluster tree of a density or a density estimate. Okay, so what's the situation here? So we're given observations x1 up to xn in some m-dimensional space and the density estimate p hat. Now we're going to define an edge-weighted graph. So the way we're going to do this is, so we're going to look at the complete graph over the data points. So we have n data points. We look at the complete graph over those n data points. And then we assign an edge weight to each edge. And what this edge weight is going to be is the edge weight for the edge connecting observations I and j is going to be the minimum of the estimated density or of the density along the edge connecting I and j. Okay, so point I, point j, we look at the edge, we have a density estimate, we find the minimum of the density along the edge. Right? That's the edge weight. Now, just formally, if I not equal to j, right, the weight of the edge is just the minimum of the density along the edge connecting points I and j. If I is equal to j, then then you have the weight of a point. The weight of a point is just the estimated density at the point. Okay, so we're gonna define this edge-weighted graph, and then I'm going to define the concept of a threshold graph. So G is this edge-weighted graph. The threshold graph at level lambda you obtain by taking the original edge-weighted graph and you toss all the edges, which have weight less than or equal to lambda, and you toss all the points, which have weight less than or equal to lambda. So the threshold graph retains those edges and those vertices of the original graph, right, for which the weight is bigger than lambda. Okay, so now we can define something I call a sample level set. So the sample level set is just the vertex set of the threshold graph, or very simply, it's just a set of all observations for which the density is bigger than lambda. Then you can also define what I call sample connected components. Those are the vertex sets of the connected components of the threshold graph, right? So again, you have the graph, you move up the threshold, edges and points will disappear, right? At some point, the graph will have two connected components, right? You get the picture, right? Okay, so now why does that make some sense? Well, note that if the observations I and j are in the same component of the sample, in the same sample connected component, then they're in the same connected component of the actual level set L of lambda comma p hat. Now, why is that? Well, if xi and xj are in the same connected component of the threshold graph, right? That means there is a path in the graph, right, which connects xi and xj, right, for which the density is bigger than lambda, right? So therefore, they're in the same connected component of the level set, right? The reverse isn't necessarily true, and here is an example. So you could be in a perverse situation, right, where this is a connected component of the threshold graph, right? This is a connected component of the threshold graph, but the density, right, has the level set of the density has this funny kind of banana form, right? It's just that we didn't happen to have any observations anywhere in here, right? And so therefore, what really should be one connected component gives us two, right? Okay, so basically we made over we might overestimate the number of connected components. And that's, I don't know any way around that. That is just the price we pay, right, of basically converting a computationally very hard problem into a computationally fairly simple problem. So just one remark. There is nothing magic about using the complete graph as the test graph, right? Because basically, what's this graph for, right? The graph just basically, you have an edge weight for each edge, which depends on the underlying density, right? And then you use thresholding, right, to find connected components. Right? You don't need to use the complete graph. Actually, that may be wasteful, right? You could just use a near neighbor graph, a minimal spanning tree of the Euclidean minimal spanning tree, of whatever. I mean, there is nothing magic about the complete graph, right? Actually, using the complete graph is kind of expensive, right? Because there's order n squared edges, right? And so simpler graphs may work just as well. Okay, so the connectivity structure of these threshold graphs is summarized by what I call the sample cluster tree. So this should be fairly obvious what's happening now. Each node of the sample cluster tree represents a subgraph of the complete graph and is associated with some density level. The root node represents the entire graph, right, and is associated with density level 0. And to determine the descendants of a node, I mean, again, it's probably, instead of going through this definition, it's easier just to say what happens. We have this edge-weighted graph. We move up the threshold level, dropping edges and points for which the density is below the threshold, right? Then eventually the graph will have two connected components, right? Well, it probably, even if there are, eventually the graph may have two connected components. Right? As soon as it has two connected components, we generate two daughter nodes of the root node, and we recurse the whole thing on the connected components. Right? All right, so this is what's happening. So here is a very simple example. So we picked, I think, 20 total points, and we didn't use a density estimate here. We just basically, oops. Okay, sorry. Oh no. Okay, let's see, I gotta flip forward here. Sorry about that. All right, so we picked, I think, 20 points, sampled from 2 Gaussians, and the density we used here is not actually estimated density. We just used the actual Gaussian densities for purposes of illustration here. Okay, so this is the complete graph over these 20 points, and the thickness of the lines indicates the minimum density along the line segment. So thick line means high minimum density. Okay, now we start this thresholding process, right? So the first edge, the edge which has the lowest edge weight, is this one here, right? So this edge gets dropped first, right? But you still have only one connected component, right? Okay, so you up the level, you keep dropping edges, and you keep dropping points till actually in this case no points are dropped. It just happens to be that way. So you just keep raising the level and dropping edges and points until you're here, right? So now you have two connected components, right? Okay. So now you recurse the procedure on the two subsets that you have, so on the two subgraphs you have so obtained. Okay. So then when you do this, when you now keep on doing this thresholding on the now we're starting the recursion on the upper cloud here, right? So the first, now as you up the threshold, there is one point gets dropped, this guy here, and a whole bunch of edges. Now why do a whole bunch of edges drop? Well, the minima of those edges, the minimum of the density for those edges happens to be assumed at this point, right? So when this point drops, right, all the edges which are incident to this point also drop, right? So you do this, you keep doing this here, and you will not find any more splits. So basically, this no matter how, as you up the level, you will always have one connected component till there is no points left. And then the same thing happens over here, right? So what would the sample cluster tree look like? Well, it just has a root node and two daughter nodes, right? One for each of the two groups. Yes.
Connected components rather than cliques?
I never thought of using cliques, so I don't know.
I mean, that's if everything in the complete is going to be connected to everything else, so there needs to be a division.
So that would be
And
that.
between every one of those guys, so you're above the ISO density contour.
How would that handle the concentric circles kind of situation?
I mean, they're just different ideas. That was just
Right. No, I never. So that would be a much stronger. That would be a much stronger condition on clusters, right? And I would assume that they would tend to get spherical. You would tend to get more spherical clusters that way, right? Yeah. No, I think that. I mean, that's actually that's actually something you might want to think about. I mean, if you want to get more spherical clusters, right? That may be a way to do it, right?
Werner,
Yeah.
you're saying that you always stay with one component. Well, if you keep on pressing the lambda
Uh-huh.
down all the way,
Uh-huh.
eventually wouldn't you start to sort of isolate the individual points? Your level sets, right? I mean, because each one is going to be one which is smallest.
Sorry, I guess I don't understand.
In
the
this
question.
example, if you increase lambda, eventually you'll break up the right cluster, right, to singletons.
Okay, don't you?
No.
Not if the minimum or maximum or whatever the density is at the
Always at, oh, I see.
No. I mean, you raise the level, right? And then once the level is above the highest density, right, then you have the empty set, right? Right.
Werner?
Yeah.
Since we've broken your flow, can you take another question?
Sure.
Are you going to tell us why there's a good reason for restricting the points to the sample points rather than simulating from the p hat to enrich them?
Yes, that is a very good point. I mean, I tried to say that before. I mean, that there is nothing magic about picking the complete graph over the data as your test graph, right? I mean, you could sample points from p hat. There may be other schemes, right, to use as the vertices of the test graph, right?
Solve your problem with a banana shape.
Yeah, so you can just have a more dense sample. The problem then becomes a computational one, right? Yeah. No, that's a good point. Yeah. Okay, so now of course we still have a little problem here, which is that these edge weights. So the weight of edge ij, right, is the minimum of the estimated density p hat along the line segment connecting xi and xj, right? And of course we don't know that, right? Okay, so there is now two approaches of this. One of them I call the hack approach, and one is a more principled approach. So a hack approach is use any kind of numerical optimizer to find the minimum over the segment, right? The simplest one, which I use in the examples here, is I just put down a grid on the line segment. I evaluate the estimated density at each of the grid points. I take the smallest value. However, there is a more principled approach, which is what Rebecca did a lot of work on in her thesis, which is based on the following idea. First of all, to construct the cluster tree, you only need the orders of the edge weights, right? The orders of the edge weights determine the topology of the tree. Right? So then for many density estimates, like if you have a kernel estimate or some other kind of mixture estimate, you can actually obtain an upper bound on the magnitude of the second derivative along the line segment. I mean, you have a Gaussian mixture in the line segment, you can find out you can get an upper bound on the minimum of the second, on the maximum of the second derivative. So then the thing is, if you have such an upper bound on the second derivative, you can actually solve the global optimization problem to arbitrary accuracy, right? If you have an upper bound on the magnitude of the second derivative, you can get arbitrarily tight bounds on Pij at the cost of additional evaluations of p hat and its derivatives. Right? So you need to get an arbitrarily tight bound. You have to evaluate the density and its derivatives at a bunch of points along the line segment. But the point is, you can make these arbitrarily tight, right? If you have, and you know the error, you know the maximum of the error, right? If you have an upper bound on the second derivative, right? And therefore, you can establish the ordering of the edge weights. All right, so now I want to talk a little bit about the connections to single linkage clustering. Well, the main reason why I do this is because we have this procedure generalized single linkage, and I just want to give some idea why this is so. So for those of you who don't know what single linkage clustering is, I mean, don't worry about that. The rest, you'll understand the rest of the talk anyways. So first of all, there is an algorithmic connection, which is that when you want to, so you have this graph G, right? And you do this thresholding and you generate the sample cluster tree, right? It's a fact that you can construct this cluster tree by applying the thresholding process to the maximal spanning tree of the graph G instead of the graph G itself, right? So maximal spanning tree is the tree that connects all the points and has the maximum total edge weight. Okay. So you do not actually have to threshold this graph G. You can compute the maximal spanning tree of the graph G and threshold the maximal spanning tree, and you're going to get the same answer. Right? So note that the maximal spanning tree with edge weights Pij is the minimal spanning tree for edge weights 1 over Pij. Actually, there's nothing magic about the 1 over any monotonically decreasing function will do. So we construct the sample cluster tree by recursively breaking short edges of the maximal spanning tree, which means long edges of the minimal spanning tree, edges with small Pij. And when you apply, this is the connection to single linkage, when you apply this thresholding process on the minimal spanning tree, on the Euclidean minimal spanning tree of the data, you get single linkage clustering. Right? So that is an algorithmic connection. Both single linkage clustering and our procedure, basically, you compute the minimal spanning tree of a graph, and then you recursively break the minimal spanning tree. Right? So that is the connection. Another connection is a little bit more mathematical. So let's consider the one nearest neighbor density estimate. So the one nearest neighbor density estimate is defined as follows. So we have X, capital X is our data set, right? X is the point at which we want to estimate the density. The one nearest neighbor density estimate at point X is just 1 over the distance between X and between the point where we want to evaluate it and the data. So the minimum, 1 over the minimum distance between X and any data point, right? Now, it's obvious this isn't such a wonderful density estimate, right? First of all, it's got a singularity at any one of your data points, right? Because you're dividing by 0 here, right? And it can't even be normalized, right? Actually, typically, people put in some normalizing factors and some powers here, but they're not really important. I mean, monotone transformations are irrelevant in this context. Okay, so now if we define the weight Pij of an edge in the complete graph as the minimum of the nearest neighbor density estimate over the edge, then the maximal spanning tree of the graph is the Euclidean minimal spanning tree. So let me say this again. Okay, so remember what the recipe was. We defined this graph, right? For each edge ij, we give the edge weight is the minimum density along the edge, right? Okay. And then we compute the maximal spanning tree of this graph, and then we threshold that, right? Now, if as density estimate, we use the one nearest neighbor density estimate, the maximal spanning tree of this graph is actually the Euclidean minimal spanning tree of the data. So this makes it very attractive to use the one nearest neighbor density estimate in this context, right? Because to evaluate the Euclidean minimal spanning tree, right, you don't have to find there's none of these things of finding minima of the density along each edge, numeric, all this stuff just goes away, right? And computing a Euclidean minimal spanning tree is actually pretty fast. All right, so I want to illustrate this thresholding idea one more time. Okay, so here is a data set. Here is a data set consisting of 2 apparent groups, a bunch of points over here, which I call the banana, and then a bunch of points over here, which I call the lump, right? So we have the lump here and the banana there. I compute the kernel density estimate, and these lines that you see here are the isoplaths of the kernel density estimate. Okay, on the right here is the maximal spanning tree of the data, right? So I compute this edge-weighted complete graph. I compute its maximal spanning tree. The maximal spanning tree is shown on the right-hand side here. Okay, so now we play the thresholding game, right? So the first edge that gets dropped is this one here. So we drop an edge and we drop a point, right? Well, the reason why we drop the point and the edge at the same time is because the minimum of the density along this edge is attained at this point, right? So you drop the point and you drop the edge, you raise the level, right? So then the next edge that gets dropped, again, you drop an edge and the point goes here, right? And so you keep dropping away, right, till eventually you drop this edge here, right, which is dotted here, so until now, we've always had one connected component, right? Then eventually, we drop this edge here, and we'll get two connected components. We get one connected component here, one connected component there. Okay, so then we recurse, right? So we apply the same procedure to the banana connected component. Again, an edge drops here, right? And then, so we get a split here, we get a split there, right? And in this case, when we proceed with the recursion to this part of the tree, there aren't any more splits, right? So you never get two components anymore. You just keep dropping points and dropping edges, but you always have one connected component, right? Okay, so now what does the cluster tree look like? The sample cluster tree. Well, we found 4 clusters, right? The lump, and then this, and this, right? We had one more split here and one more split there. So we found, in this case, the tree has 4 leaves, right? And so this is what it looks like. Okay, so now when you interpret these trees, you have to be a little bit careful, because of the daughters of any node automatically have to be at the same level, right? Because they're at the level where the connected component was broken, right? So you cannot actually, so basically the levels of these nodes tell you the level of the valleys, right? Where the break happens, right? The valley of the height of the peaks is not actually encoded in this graph here, right? So you can't really tell how pronounced the valleys are, right? Because you don't know how high the peaks are, right? You just get the bottom levels of the valleys, but you don't get the tops of the peaks. Another comment here is that you see we actually missed one connected component, right? There is one more mode here, right, somewhere in here, right, which we didn't find, right? Well, just because there didn't happen to be any data points there, right? Now, I think that is not a really serious problem, because, I mean, there aren't any data points here, and this mode seems more like an artifact of the density estimation procedure than something that you really would be worried about. Okay, so now what does this tell you here? Well, so ideally what we would have liked to find, right, is a tree which has 2 leaves, right? One for the lump and one for the banana, right? Now it so happened, because of the variability of the density estimate, right, because of the sampling fluctuations, we actually ended up with 4 leaves, right? The banana was broken up into three parts here, and then we had the lump, right? So now what can we do about that? So somehow we need to prune this cluster tree, right? We need to prune the sample cluster tree and try to get rid of modes which we think are spurious, in the sense that we think they're actually caused just by the variability of the estimate. Okay, so somehow we have to be able to measure the prominence of a mode, right? So how much does that mode stick up from the valley, right, which separated from the rest of the data, right? And so here is the measure that I did not invent this concept of excess mass. So other people had invented that already. So the excess mass, so I go back to this example here. So the excess mass of this node of the cluster tree is just, so remember we raise the level from 0, we get 2 connected components here. Then we measure the prominence of this connected component just by the area of the density, right? Or by the volume of the density sticking above the valley floor, right? And so mathematically, the excess mass is defined as the integral over the area of the feature space associated with this node of the density minus the level. So this is just a way of writing this up, of writing down this area here, right? So then the question is, how can we actually compute that, right? Well, so here is so here's a hack approach. Well, we don't have observations. So you would use some kind of a Monte Carlo estimate, right, to estimate this thing, right? But we don't have observations from the Lebesgue measure, right? But we do have observations from P of x. Well, so you just multiply with P of x and you divide by P of x, right? And then you get, this is the sample analogon. So you sample over all the you average over all the observations which are in the corresponding connected component, and what you average is 1 minus the level over P hat of xi, right? So see, when you divide this thing here you divide by P of x and you multiply by P of x, right? Then you get 1 minus lambda of n over P of x, right? P of x dx, and that integrating with respect to P of x, you know how to do because you have points from P of x, right? So this is just a simple a Monte Carlo estimate. Okay, so this is how we measure the prominence of modes, or measure how much a peak sticks above the valley and how big the peak is, right? Okay, so what we're gonna do now is we're gonna pick some threshold for the excess mass, basically saying, well, we're only gonna consider peaks significant, right, which have an excess mass bigger than blah, and so we choose some mass threshold, and then we remove all the nodes which have excess mass less than gamma, which is this parameter that we've chosen, and their incident edges. Well, so we have the sample cluster tree. We remove all the nodes which have excess mass less than lambda, remove their incident edges. Now that tree may no longer be binary, right? Well, so then we just binarize the resulting tree by splicing out degree 2 nodes. Okay. Now there is actually another way to look at this, is where you do the following. Okay, so you have your graph and you start thresholding. Eventually you get 2 connected components. So then you ask yourself, do both of these connected components have excess mass bigger than lambda? If they do, well, then we make a split. If one of them has excess mass less than lambda, then we don't do a split. Right? So basically, instead of first building the whole sample cluster tree and then pruning it back, right, you basically do the pruning during the tree construction. Right? And the key thing here, why this actually makes sense, is that this excess mass measure is monotone. So if you take any node, so if you go up the tree, right, the daughters of any node have a smaller excess mass than the node itself, right? That's why when you do this pruning, you never end up with any kind of dangling edges or vertices, right? So this monotonicity is an important property for the pruning. Okay, so now here we go back to our little example here. And so what I've written here is I've written the Rand excess masses under the next to the nodes. By the Rand excess mass of a node is, I mean, the minimum of the excess masses of the left daughter and the right daughter, right? So that if that is big, that means the split gave you 2 substantial peaks, right? If that is small, right, that means at least one of the peaks was just a little wiggle, right? That's the intuition, right? So then you see, well, so the Rand excess mass for this node here is 0.23, right? So basically you have substantial pieces on both sides, right? Then for the other splits, it's 0.01 and 0.001, right? So that's clear that the modes that you identify here are much less prominent, right, than the modes you got there, right? Okay, so actually I only have 10 minutes, so I'm going to skip the first example here, and I want to give you at least one real example, which is acute lymphoblastic leukemia data. Those are data which I think many people use for illustration purposes. I picked those as an example here because they're really high-dimensional data. So the data set that I used has 215 subjects with this kind of leukemia, and somebody grouped them into 6 known ALL subtypes, so subtypes of this particular kind of leukemia and other. And so we have the expression levels for 12,000 plus genes, right, for these 215 individuals. So there is 12,000 dimensions and 215 observations. And so the question that I'm asking myself is, how well can we recover the grouping, right? Now, that's an important thing to realize. If you want to empirically evaluate clustering procedures, you have to have labeled data, right? Right. Otherwise, I mean, you don't know what the clusters are, right? And of course, when you simulate data, right, you can figure out what the true level sets are, right? And you can evaluate it, right? But on non-simulated data, they have to be labeled. Okay, so before I clustered this thing I did some pre-processing. I chose the 1,000 genes with the highest variance. So the idea being, well, if there is essentially no variability in the expression levels over the 215 people, right, then this is probably not very useful to identify groups. And then I normalized the expression profiles for each individual, for each of 215 subjects. I normalized the expression profiles to have mean 0 and variance 1. So that means then that a small Euclidean distance means high correlation between the expression profiles. Right? Okay, and I did something totally naive. I just took this 1,000-dimensional data. I used the one nearest neighbor density estimate. So basically, the maximal spanning tree is I used the one nearest neighbor density estimate. Then we just see what happens. Okay, so now if we look at the Rand excess masses of the nodes of this sample cluster tree in decreasing order, so what you get is, remember, so what do these numbers measure? Remember what they measure. So for every time you get a split, you look at how prominent is the right peak and how prominent is the left peak, and you take the smaller of those two. So this number being large means the particular splits separates two substantial peaks. So if you look at that, the numbers are 36, 27, 21, 14, 8, 5, 5, and then there is bunches of 5s and 4s and 1s, etc. So just by eyeballing this set of numbers, I decided, well, I'm going to set a cutoff here. So you have 4 splits, so you have 5 clusters, right? Okay, so here is the sample cluster tree, and more importantly, this is not all that, doesn't give you all that much insight in this case. Hello? Okay. So here is the table of the ALL subtypes versus the clusters. So here are our 6 subtypes, 1, 2, 3, 4, 5, 6, and other. And then here are the cluster labels, right? Okay. So now if you look at this at this table here, you see that the procedure actually can identify T all, right? So T all corresponds to cluster label 3, and let's see, it can identify pretty well this one here, E2A PBX, that corresponds to cluster 4, right? But there is some overlap with other clusters, right? It can identify TLAML1, right? Again, there's a little bit of overlap with others here, right? It is not successful in isolating the other subtypes. So this is a partial. But I mean, it's kind of remarkable. I mean, this is 1,000-dimensional data, right? And 215 observations, right? And it actually pulls out those 3. It identifies those three subtypes. All right. So let me summarize and talk a little bit about future work. So just running through the main points of my lecture again. So the goal of clustering is to detect the presence of distinct groups. The premise of non-parametric clustering is that groups correspond to modes of the feature density. The structure of the collection of level sets of the density is described by the cluster tree. That's the population characteristic of interest that we're trying to estimate. And modes of the density correspond to leaves of the cluster tree. The cluster tree is defined recursively, and that suggests a recursive partitioning method for its calculation. So the approach that we pursue is a plug-in approach. We estimate the cluster tree of the feature density by the cluster tree of a density estimate, right? Now, it's not at all clear that this is the best thing to do, right? Often the rule is sort of, well, don't use plug-in estimates. If you want to estimate something, just go and estimate it directly, right? Don't do this plug-in thing, right? But we just didn't have any better ideas. Okay, for some densities, piecewise constant over rectangles, or in general piecewise constant estimates, you can compute the cluster tree exactly. For others, we have to approximate the cluster tree by the solution of a graph problem, which gives this generalized single linkage clustering. this generalized single linkage clustering recipe can be applied to any density estimate, kernel estimate, new neighbor estimates, whatever you name it, mixture estimates. It can be applied to any density estimate. The sample cluster tree will have spurious branches reflecting spurious modes of the density estimate, but we have a way of measuring the size of the branches and allowing for subjective pruning of the tree. Okay, so in terms of future work, what is there to be done? Well, so obviously feature selection or dimensionality reduction. That's an important point, right? So that's the point that many of the talks in the workshop have previously addressed, right? And so one idea is if you have labeled data, right? Well, how would you do pre-screening? Well, you just do t-tests for each of the variables, right? And then you toss all the variables which have the least significant t-tests, right? Well, that's not so clear what to do here because you don't have any labels, right? So in principle, one could think of like finding variables which are the least Gaussian, for example, right? Or selecting the variables which are farthest away from unimodal, right? That would be something to try. We haven't tried that. Alternative density estimates. So what I'm thinking of is, boosting density estimates, projection pursuit density estimates. There are a number of things one could try. Alternative methods for estimating level sets. So actually, I don't have time to talk about this now. And the most important one, or an important one, is more principled approaches to pruning the sample cluster tree, right? So somehow what's unsatisfactory about this is to basically have to sort of just look at these numbers and then sort of subjectively set a threshold, right? So maybe by using bootstrap ideas, we can come up with a way to have a more data-driven. We can come up with a more data-driven method of setting the threshold, and we actually do have some ideas about that. Thank you.
Yeah, so a lot of appeal in what you're doing. The only unfortunate thing seems you have to start with a density estimate,
right,
as you pointed out. But it seems like there's kind of three aspects. You have data, and you have some notion of connectivity pattern.
Correct.
And then you have a very nice procedure for analyzing that.
Right.
And I'm thinking a little bit about spectral clustering methods, which in some sense don't do a density estimate, but they somehow try to find connectivity patterns. And then they have kind of dumb methods for rounding into actual clustering. And so it might be a nice marriage of like a sort of spectral relaxation as a first phase to get connectivity patterns, and then your sort of procedure, which is a much more sophisticated way to turn that into clusters.
Huh. Yeah, that sounds good.
I know you have a spectral clustering expert in your
I know,
department,
right.
so
No, definitely. Yeah, I mean, I know about that. Yeah, but we haven't pursued that. Yeah.
Have you thought at all about when you start with your point set and want to make this tree? So it seems to me the reasonable objective would be to try and define a probability distribution on the space of trees. Let's say some trees. I mean, the data is not going to tell you exactly which tree. It's only going to. It only
Right.
really tells you a tree with a certain. I mean, the most you could expect to get from the data is a certain kind of estimate of how likely it is that that tree comes up. So it seems to me it'd be a nice framework if one could actually get a probability distribution.
Yeah, I never thought about it. And I would have no clue of doing that because there's potentially a huge number of trees, right? And I mean, then so I guess what you're saying is trying, instead of just coming up with a tree, right, coming up with a collection of plausible trees and probabilities associated with those. Or
I was thinking of the kind of thing that people do in phylogenetics,
Okay.
which is sort of along those lines.
yeah, that's actually that's something we actually have thought about some. Yeah, we just haven't done that. Yeah.
So one thing that gets a lot of people excited in computer science is these ideas of like random projection to reduce the dimension. And so, for example, like if you take endpoints in large dimension, you can find projections of very low dimension that actually preserve the pairwise distances.
Right.
So it's called the Johnson-Leidenstrass.
Right.
I'm sure you know about this. And so people use this a lot for speeding up clustering algorithms and things, because what it says is that you can operate in the space of much lower dimension without. So if your density estimate is based on some kind of Euclidean distance, or as you said, you use the nearest neighbor thing, have you thought about perhaps combining your approach with this kind of projection ideas to either speed up computations or perhaps get accurate estimates of the density?
Yeah, no, actually, I've thought about this. We haven't done anything. So just one comment. I mean, if we have, so in this example of the ALL data, right, we have 250 something points, right, and then we have 1,000 variables. So, but really, the points only are in the 214 dimensional space, right? And so then the question, so you're not really talking about random projections of 1,000 dimensional space. You're talking about random projections of 215 dimensional space or 14 dimensional space, right? And then it's actually not clear to me how, I mean, I don't have any experience how well, let's say I picked a random 20 dimensional subspace, right? I don't have any really good intuition of how much of the information this would actually preserve, right?
Because my experience just going to workshops, at least if I believe what people say when they do document classification, I've been to a lot of talks at IPAM in the last few years, people say that you can really reduce the dimension by this kind of ideas so that, you know, you can save a lot of computations by doing it this way.
Well, I guess the saving computation, I don't know how important that is, because the computation is linear. I mean, you're computing distances basically, so the computation is linear in the dimension, right? So the dimension isn't really what's killing you. I mean, what's killing you is the sample size, right? Especially if you start with a complete graph, right? Because you have a lot of edges, right? And then you've got to find the minimum along each of those edges. So that's really, that's the killer, is the sample sizes. I mean, algorithmically, right? Or computationally, the killer is the sample size, right? Not the dimension so much, right?
I was going to say that this is very reminiscent of Mike Minotti's mode tree. Do you know of anything?
So the mode tree you get by changing the bandwidth, right? Right. No, but the two things actually could be combined in some way, right? Because you could think of generating like a parametric family of trees, right? Where you change the bandwidth of your estimate, right? And that's something I've thought a little bit about, but we haven't done anything, right?
Another approach to dealing with sort of this idea of sampling variation is maybe just to jitter the points a little bit and recompute the mode trees, or recompute the trees.
Yeah. Yeah.
One aspect which I think the density aspect is, looking at it that way is beautiful, but one aspect which somehow isn't captured, which is that things are dependent on the representation, or equivalently, the clustering does depend on the metric. So that, for example, if you make a non-linear transformation of the data, then you pick up a Jacobian,
right?
And then the whole structure changes. Have you thought at all about, sort of, again, like in the sense of parametric families of trees, but not in the sense of changing the bandwidth, but in thinking of families of one-to-one transformations of the data?
That is something we haven't thought about at all. I mean, the affine transformations, non-singular affine transformations, when I say they don't matter, that's actually not quite true. I mean, the cluster tree of the density, right? The topology is invariant, but any density estimate is going to use a distance measure, right? And so, but no, about sort of systematic ways of using, let's say, nonlinear transformations of the data space. No, we haven't thought about that at all.
Okay, so last question.
Not so much a question as a comment. In, I think, 2006, in the Annals, Bing Lee and a couple of other authors proposed a method called contour regression for doing dimension reduction. And as I recall, the heart of their method is a graph structure very, very similar to the kinds of things you were doing. And my intuition is that you might be able to make good progress by marrying together their contour regression ideas with your ideas to address the first point under future work.
Okay. Okay, thanks.
All right, I'm pretty sure that we have a lot of questions, but we need to lunch and take photos, so let's thank speak again.